So the density of a metal is 8.9 gram per cm cube at 20. In fact, there was an omission. The initial temperature isn't 20, but it's 0. Okay, because if there is no change in temperature, then the density must be the same. So the density of a metal is 0 degrees Celsius. Find its density at 20 degrees Celsius if the linear expansivity is 0.00002 per Kelvin. So initial temperature, T initial is 0, T final is 20 degrees Celsius. And initial, hey, Johan, please mute yourself, eh? So the initial density is 8.9 gram per cm cube. So we are to determine the density final at 20 degrees Celsius. Okay, the point is that one of the factors which affect density is temperature. When you increase temperature, density decreases. The reason is that when you increase temperature, particles gain enough energy, and so their kinetic energy increases. If the kinetic energy of a particle is increasing, then they will space out. It's like having more energy to run away. They will space out. When they have, that is why when temperature increases, volume also increases, because kinetic energy of molecules or particles, okay, is increasing. So when volume increases, it will decrease density. Density is aggregation of particles within a certain volume. So when we close up, our density increases. When we space out, our density decreases. So the moment you increase the temperature, volume would increase and density would decrease. So there must be a relation between density, volume, and change in temperature to solve this. And this is a relationship we know. We know that density is equal to mass over volume, meaning that density is inversely proportional to volume. So an increase in volume will decrease density. Okay, and this is the situation. So at for two different densities, rho 1, okay, will be inversely proportional to V1. This is at constant mass. Don't forget, it is the same substance whose temperature is increased from 0 to 20. So the mass, okay, isn't different. It's the same mass. But we are looking at what will happen to the densities as we increase temperature. And so rho 2 will also be inversely proportional to 1 over V2. Okay. And when you divide density 1 by density 2, or the other way around. So if we have rho 1 divided by rho 2, this will be equal to 1 over V1 times V2 over 1. So rho 1 on rho 2 is given as V2 on V1. Okay. Now, we've also learned cubic expansion, that if you have an object and you increase temperature, its volume will change because there will be a linear increase in the length, breadth, and height. So the moment you change the temperature, volume would also change. And V1 V2 is equal to V1 plus change in volume, meaning the final volume will be equal to initial volume plus the change in volume. Thus, we derive an equation for it that V2 is equal to V1 plus volume or cubic expansivity times the original volume times the change in temperature. So V2 is equal to V1 out, 1 plus volume expansivity times delta T. So this is the expression for V2, which we will substitute here. So we substitute this in place of V2. You have rho 1, rho 2 is equal to V1, 1 plus gamma delta T on V1 again, where V1 would cancel out. Okay, so it simply means that rho 1 on rho 2 will be equal to 1 plus cubic expansivity times change in temperature. Okay, and we've learned relationship between cubic or volume expansivity and linear expansivity. Cubic expansivity is equal to 3 times linear expansivity. So this will be equal to 1 plus 3 times. We're given the linear expansivity of the metal. Charlotte, what's the value? 0. Charlotte, what's the value of linear expansivity? 0. What?
0.00.
4 zeros. I know it's 4 zeros.
21. Yeah.
Look at it again. 0.0000002.
21.
No, that is per Kelvin. It's
okay.
2. Okay. Therefore, you just would have to make lambda rho 2 the subject. So rho 1 on rho 2 is equal to 1 plus 0.00006. Okay. Now you are given the rho 1 8.9. So determine rho 2. Class, do it for me. Once you have rho 1 to be 8.9, find rho 2, and that will be the second density as a result of the change in temperature. So calculate it for me. When you finish, you call your answer out for the house. So we move on. Amma, what's your final answer? Or Charlotte? I have 16 of you in there. What's the final answer?
The final answer is 8.794. So good.
8.794 gram per DMT, meaning there will be a little change in there. Okay, so this is just the question. It's such a nice application question. Okay, then the second question. These days, class, are you tired of solving questions? Are you tired?
No, please.
But I give questions and the response is just a few of you. Amma submitted. Jeriel, I didn't hear from you. Charlotte, I didn't hear from you. Ekuya did. Akuya Watma, I know will do it at the. I know her concerns. Asumanin, it never came. Alvina never came. Rama, no. Festus, I think I saw that of Festus. Jeriel missing in action. Nana Oheneba, Othniel, Teresa, Tucci. Are you tired of solving questions? Maybe yes. But the point is that if you don't find time to try your conceptual understanding to solving problems, you will not understand. So I beg you try as much as possible to do your part, right? First, your hand is up.
Sir, please, when you substituted the linear expansivity into the equation, you didn't have a change in temperature.
Oh, thank you. You're right. So 1 plus, this is, gamma is this, 3 times. So times 20. Thank you. Times 20. So it's actually this times 20. And you play around, blah, blah, blah. And then, so meaning this denominator must change. So multiply it for me. 20 times 0.406 plus 1. First, just give it to multiply this by this, add that to 1, and then give me the results. Somebody else must also do it so that we don't waste time. Yes, Festus.
The 8.89.
No, I mean, I was just rather looking for the 0.0012. Okay. So that when you divide 8.9 by 1.0012, you have 8 point. Is that 8 point what? Eight points.
8.89. 88.
8 points. Approximately 8.889. 8.889 gram per cm3. Okay, so thanks for the correction. Now the second question wasn't also difficult. Yes, if you had actually spent time to go through it, it's not a difficult question. You are given 2 strips, I think brass and iron, of different expansivities, and you are asked to find the temperature at which the 2 lengths will be the same. Okay, so we'll just brush through this quickly and then let me retrieve the question. Good. A certain bimetallic strip is made of brass and iron. It's made of brass and iron with linear expansivities. So alpha of brass 0.1.9 times 10 to the power -5 per Kelvin. Then alpha of iron, this is also 1.2 times 10 to the power negative 5 per Kelvin. Then at a certain temperature T, the length of brass is 50. So at T, initial temperature T, L of brass 50. At the same temperature, L of iron is 60. If the bimetallic strip is heated, at what temperature would the lengths of the two metals be equal? Okay, so at what final temperature would them have the same length? Okay, express your answer in terms of T. So L2 for brass, L2 will be equal to L1 out 1 plus alpha times delta T. Okay, therefore L1 will be equal to 50 times 1 plus 1.9 times 10 to the power negative 5 delta T. Change in temperature, we don't know. Okay, this will be for L2 for brass. Then for iron, L2 would be equal to 60 times 1 plus 1.2 times 10 to the power negative 5 delta T. Okay, now we know the initial temperature to be big T. So at what temperature would the two metals have the same length? So when L1 is equal to L2, we'll have 50 times 1 plus 1.9 times 10 to the power negative 5 delta T to be equal to 60 times 1 plus 1.2 times 10 to the power negative 5 delta T. Okay, so you equate them to find delta T. You equate the two because we are looking at the point where they will have the same temperature. When you equate delta T, I think will be equal to, if you solve this, you have delta T to be equal to 10 to the power, I think 5 over, is it 2.3 or so? Okay, I don't want to go through this. As for delta T, you can find it. Okay, but when you solve this equation, you have delta T to be equal to this also. So knowing delta T, you know delta T to be equal to T2 final temperature minus T initial. Okay, therefore T2 would be equal to T1 plus delta T. We found delta T and T1 was given to us as big T. Okay, therefore this will be T2 will be T plus 10 to the power 5 over 2.3. This, some of you express it in whole number and you had I think, is it 40,000 something. But the answer that was presented in the book is this. Okay, so it actually wasn't a very difficult question. Either you leave your answer in this form or how some of you divided 10 to the power 5 by 2.3 and then added that to T. Okay, so class, it's you whenever you are given a question, just think through. If you think you have problem, you can contact me. Sir, please, can you guide me in how to look at this question? And we can do it. Okay. So it isn't any difficult problem. Please, is there any question? Is there any question, or we can move on? Okay. So if there is no question, I think Amma.
Sir, please, why is the denominator just 2.3?
No, I'm saying that if you solve this, you have something like this. Okay. I don't know, maybe that is not, but anyway, let's solve it. Okay. For the benefit of the rest of you, let's solve it. So when 50, 60, we can reduce by canceling out the zero. So we have, let's multiply through by 5. So 5 plus 5 times 1.9. Please help me out in a multiplication quickly. What 5 times 1.9? And this is 9.5. So we have 9.5 times 10 to the power negative 5 delta t to be equal to, then we come to the right hand side. 6. Okay, 6 plus 6 times 1.2. That will be 7.2. So 7.2 times 10 to the power negative 5 delta t. Okay, let's group like terms to find delta t. So we have to send this to the other side. So we have delta t, or 10 to the power negative 5 delta t times 9.5 minus 7.2 is equal to 6 minus 5, which is 1. Okay, then you make delta t the subject. You have delta t to be equal to, what is 9.5 minus 7.2?
Mr. Yeah,
Hello?
please, I can't see your screen.
Oh, please, is it a general problem?
No.
So please rejoin. Okay, I'm sure that will be sorted out. It will be a network challenge from your end. Okay.
Okay, thank you.
Okay, so when you subtract 7.2 from 9.5, the answer is 2.3. Okay, so let's be systematic to help others. So we have 2.3 times 10 to the power negative 5 delta t is equal to 1. Then we are looking for delta t. Delta t is therefore equal to 1 divided by 2.3 times 10 to the power negative 5. And 10 to the power negative 5 can be positive 10 to the power 5 over 2.3. So, Amma, the value is still the same. It is exactly as I quoted. Okay. So there's a change in temperature. Therefore, the final temperature T2 will be equal to the initial temperature T plus the change in temperature 10 to the power 5 over 2.3. So it wasn't a difficult question. It wasn't a difficult question. The only thing is that maybe sometimes our problem is that with physics questions, the moment the question is given, then we begin to flinch. Okay, and we think, oh, this is difficult. What manner of question is this? But colleagues, if you really spend time to read through, think through, it's a doable question. Okay, so when I give you a question and you, on a face value, you think it's difficult, please, you can call me or contact me on WhatsApp for explanation, and it will guide you to solve it. Is that okay?
Yes, please.
Okay. All right. Let's move to calorimetry. measurement of heat. Calorimetry is about the measurement of heat using the calorimeter. The calorimeter. So calorimetry is measurement of heat. And then the calorimeter is an instrument, a very nasty instrument that is used to measure heat. Okay. But before that, let me find out from some of you. Can you tell me about the heat capacity of a material and what we also mean by specific heat capacity? So I want your view on these two: heat capacity, and then specific heat capacity. Heat capacity and specific heat capacity. Any idea about these two concepts? What is the heat capacity of a body and what is the specific heat capacity of a body? Yes, anybody to share his or her view with us whilst I take notice of attendance. Please, any idea on heat capacity? Lizzie, go ahead.
Yes, please. Heat capacity of a body is the energy required to raise the body to 1 Kelvin.
Okay, so, but Lizzie, my follow-up question is that what energy?
Heat energy.
Exactly. So, usually go be specific. Okay.
Yes.
Please, a minute. Attendance. So when we talk about the heat capacity of a body, we are referring to the quantity of heat energy that is required to change the temperature of a body by 1 Kelvin or 1 degree. Then what is specific heat capacity of a body? What we then mean by specific heat capacity of a body? Is it the same, Lizzie? Lizzie, over to you. Give us your view.
Okay. Specific heat capacity is the heat required to raise a unit mass of a substance to 1 Kelvin.
Okay, so here you are referring to a unit mass of a substance by 1 Kelvin. Okay, so Lizzie, what is the difference between heat capacity and specific heat capacity? Can you tell us any difference between the two?
Yes.
Okay, share with us.
Heat capacity, the change required to raise the body is only through 1 Kelvin, that's the temperature. But in the specific heat capacity, there is mass attached to it, including the temperature.
Okay, thank you. All right, so class, listen. You see, materials are different. The difference in materials has to do with the difference in their atomic composition. Solids are not the same as liquids. The elementary explanation or design of what a solid is, solids are completely, they are tightly packed. Liquids, a bit, there is space. As for gases, spaces. So materials are different. And so if we pick solid, if we pick liquid, if we pick gaseous, sample of them, and we want to heat, supply these three substances with a certain amount of heat, the amount of heat energy required to heat solid will certainly be different from the amount of heat energy required to heat gaseous. This is because of their different atomic composition. Even for the same substance, pick water, the quantity of heat energy required to heat a cup of water, and then a bucket of water, would they be the same?
No, please.
No, because you see, a bucket of water has huge mass or particles, whereas just a cup of water, the mass or the particles are fewer. So it means that even for the same substances or material, if you choose different masses, they will all require different amounts of heat energy to raise their temperature. Please, when to raise, that is to increase, and to drop, decrease their temperature by 1 degree Celsius or 1 Kelvin. So when we talk about the heat capacity of a body, it is the amount of thermal energy required to change the temperature of a substance by 1 Kelvin. Okay, so here we are not interested in any mass, but the amount of thermal energy or heat energy. Please jot some points down. Okay, the amount of thermal energy required to change the temperature of a substance or material by 1 Kelvin or 1 degree Celsius is what we are calling as the heat capacity of a substance. The heat capacity of a substance is represented by the letter capital C. Capital C. And this can be determined by capital C, which is the heat capacity of a material, is equal to the quantity of thermal energy, K, required, that must be absorbed or liberated. Okay, either we are absorbing the heat energy or it is losing, liberating it in order to change its temperature. So the heat capacity of a material is given by Q. Other books also use H for thermal energy, divided by the change in temperature. So where C, big C, is equal to the heat capacity Q equals thermal energy or the heat energy. And delta T is equal to change in temperature. Okay, therefore, the thermal energy that must be absorbed or liberated to change the temperature of a body by 1 degree Celsius Kelvin is given by the product of the heat capacity of the body and then the change in temperature. So this is equation 1. Please Is there any question? So, because different substances have different atomic composition and they will all require different amounts of heat energy or thermal energy to change their temperature by 1 Kelvin. Okay. Now, we want to then look at if I have a unit mass of substance, okay, 1 kilogram mass of water, 1 kilogram mass of aluminium. Don't forget, with heat capacity, we are not interested in any mass. But this time around, I understand that different materials have different heat capacity. They will require different amounts of heat energy to raise their temperature by 1 degree. Now, if I have a unit mass, okay, if I have a unit mass of the substance, what will be its specific heat capacity, or what will be its heat capacity? So instead of being interested in the general heat capacity, which has nothing to do with mass, if I know the heat capacity of substances for their individual masses, unit masses, then when you give me any other mass, I can use that to calculate the total heat capacity of the substance. Example, you are giving me 10 kilogram of water. Then the question is that calculate the amount of heat, thermal energy that must be supplied to 10 kilogram of water in order to change the temperature of this by 1 Kelvin. It will be easier. Okay, this calculation will be easier for me if I know the heat capacity of any 1 kilogram mass of water. If I know the unit mass of water, then all that I do is that multiply whatever I know by 10, and I have the general heat capacity of 10 kilogram of water. Class, I hope you are following me.
Yes, please.
Okay, so it means that this knowing the specific makes it easier than just the general. And so we talk about specific heat capacity of substances. Specific heat capacity of substances. So if substances have different heat capacity to change their temperature, then I must know what the heat capacity of maybe aluminium, water, petrol, and all other substances. Knowing that would help calculations. Okay. So for specific heat capacity, as Lizzie said, we are referring to the quantity of heat energy that must be absorbed or liberated to change a unit mass of a material by 1 degree Celsius or Kelvin. To change a unit mass. And a unit mass, we are referring to either 1 kilogram or 1 gram. Of course, the moment if you know 1 kilogram, you can determine for 1 gram. If you know 1 gram, you can also determine for 1 kilogram. So this refers to a specific mass of 1 kilogram or 1 gram. So the quantity of heat energy that is required to that must be absorbed or liberated to change the temperature of a unit mass of a substance or material by 1 gram, by 1 degree Celsius or 1 Kelvin. The specific heat capacity of Water, for instance.
Mr. Dear,
Hello.
please can you repeat the definition for specific heat capacity?
Okay, so the specific heat capacity of a material or a substance is the amount of heat energy that must be absorbed. When you absorb it, it would increase the temperature, or liberated. When it is liberated, it will decrease. Okay, so the quantity, the specific heat capacity refers to the amount of heat energy that must be absorbed or liberated to change a unit mass of a substance by 1 Kelvin or 1 degree Celsius. That the amount of heat energy that must be absorbed or liberated to change a unit mass of a substance or a material by 1 Kelvin or 1 degree Celsius. Now, when a material absorbs a certain amount of heat, okay, absorbing it would increase the temperature. When the material liberates, it is like putting something in the freezer. It will give out the heat energy, the internal heat energy, and it will drop it. So we are looking at either increasing it or decreasing it.
Thank you so much.
Welcome. So water, for instance, has a specific heat capacity of. So please, before we talk about that of water, let's look at units. Thermal energy. The SI unit for thermal energy is in joules. You want to determine the SI unit of heat capacity. The SI unit of change in temperature can be Kelvin or degree Celsius. Don't forget the change for Celsius and Kelvin scale, it is 1:1. Therefore, the SI unit of heat capacity, big C, is equal to Joule per Kelvin or Joule per degree Celsius. Okay. Then we'll derive that for specific heat capacity. So as I was saying, water has a specific heat capacity of 4,200. Meaning that what this means is that 1 kilogram of water, 1 kilogram mass of water must absorb or liberate, must absorb or give out 4,200 joules of heat energy to change its temperature by 1 Kelvin or degree Celsius. So explain what it's meant by water having a specific heat capacity of 4,200. What it means is that water must either absorb or give out 4,200 joules of heat energy to change its temperature by 1 Kelvin or 1 degree Celsius. Aluminium, on the other hand, aluminium has specific heat capacity of, I think, 980. Adjoa, if aluminium is said to have specific heat capacity of this, okay, can you tell us what this value means? Adjoa Asante Otubia. Or let me make it general. I have explained to you what it means by water having specific capacity of 4,200. If aluminium is said to have this as specific heat capacity, what does it mean? Anybody, the floor is open to all. I have 20 of you in the house. Oh, just try, just give it a try. Anybody can do that. Hey, Jeriel, Calvin, okay, Charlotte.
Okay, so please, it means that aluminium must absorb or give out 980
You
in order to change its temperature.
by
1 Kelvin.
all degrees. Exactly. So aluminium must either absorb or give out 980 joules of heat energy in order to change its temperature by 1 Kelvin or 1 degree Celsius. So that is it. Heat capacity is the amount of thermal energy that must be absorbed to change the temperature of a material by 1 degree Celsius or 1 Kelvin. All right. So if heat capacity, big C, has nothing to do with any specific mass, general. And so if I have 10 kilograms of a material, its heat capacity is equal to the quantity of thermal energy that must be absorbed divided by the change in temperature. And so Q is equal to C times delta T. Now, if I know the specific mass, then I can easily calculate the heat capacity. So the heat capacity of a material relates to its specific mass by this formula. And that is heat capacity is equal to specific heat capacity small c, okay, times the mass. So all that I'm saying is that if I have 10 kilograms and I want to determine its heat capacity, the moment I know 1 kilogram mass, I can easily multiply 1 kilogram mass, okay, by the total mass. If I know the heat capacity of 1 kilogram, all that I need to do is to multiply by the mass. So I'm giving 10 kilograms of water to calculate for its heat capacity. Knowing the heat capacity of 1 kilogram mass of water, which is 4,200, times the total mass, which is 10. And this implies that the heat capacity of 10 kilogram mass of water will be equal to 42,000 joules. So heat capacity relates to specific heat capacity by this formula. Big C is equal to small c, which is the specific heat capacity, times the total mass. And so therefore, any quantity, when we substitute this into this relation, we have the quantity of thermal energy that must be absorbed, okay, or liberated of a material to be equal to M times small c times the change in temperature. This is the formula that is used to calculate the total amount of thermal energy that must be absorbed or liberated okay, by a substance. Jema, yeah. Charlotte, go ahead.
Mr. Dia, so please, does it mean, please, can you hear me?
Yes.
Okay. So please, does it mean that specific heat capacity and heat capacity are both represented by C?
One is heat capacity is capital C. Specific heat capacity is small letter C.
Okay.
Oh, the reason is that they are almost the same. The only difference is that one is specific to 1 kilogram, a unit mass. The other one, big C, is like there is no specific mass involved. That is why for X kilogram of a material, if I know 1 kilogram, I can easily calculate the heat capacity for the X. That is why they are related. Are you okay? Charlotte, are you okay?
Yes, please. Thank you.
Please, class.
Yes, please. Thank you.
If you are not clear with something, pay attention and then just ask. So this relation, which is Q or H is equal to MC, where Q is the thermal energy that must be absorbed to make the change. Small M is the mass involved. And small c is the specific heat capacity of different materials. And then delta T is the change in temperature. So if you want to calculate the thermal energy that must be absorbed or liberated to change the temperature of a material to so and so, this is what you need to use. Okay, this formula is applicable to only when there is a change in temperature, but not a change in state. We cannot use this for a change of state. It is only used for when there is a change in temperature. All right. Now, substances, you see, whenever the sun is scorching, solids are easily heated. So metals, stones around easily get heated. Meaning, what it means is that small amounts of thermal energy or heat energy can easily change the temperature of solids. So solids generally have very low heat capacity. Liquids, on the other hand, have relatively higher heat capacity. Okay, that is why, and this explains the reason why, you see, on a scorching day, when the sun is shining and the environment is very hot, you want to quickly take a dive or swim in water, forgetting that if the environment is so hot, it is the same sun that is heating the environment and the water body. Meanwhile, you think you can have comfort in the water than being on land. Okay, maybe you haven't thought of why that difference. If the same sun is hitting your room, wherever you find yourself, you are forgetting that the water is not covered, yet you want to find solace in swimming in water. You haven't thought of it. But the reason is that because liquids or water has a very high heat capacity, what it means is that water will require a lot of thermal energy to change its temperature. So when the weather is hot, that temperature or that heat energy from the sun, which is making the weather hot, is not enough to change the temperature of water to that temperature you are so discomfort or you are so uncomfortable about. That is why when you dive into water, you realize that it feels so cool compared to when you were sitting under the shed. Please, are you following me?
Yes, please.
It is because water has a very high heat capacity. Water will require a lot of thermal energy to change its temperature than solid. I don't know if you have visited the river or the pond in your village before or near to your house. In the early morning, if you have fresh water in a river before, you realize that in the morning, when the environment is so cool, okay, whenever you fetch water from a river, or even your tap, the tap in your house, you realize that the tap still feels very warm. Please, true or false?
True.
When you fetch water from the nearby river or from your tap in the morning, the tap or the river feels very, very warm. Meanwhile, in the morning, the temperature has totally gone down. And you may think, because you are even feeling cold, going into the river will be a problem. Then, on the other hand, in the evening, so in the morning, there is sunset. But in the afternoon, rather, when the temperature is so high, weather is so hot, you go to the same river bodies, and this time it feels so cool, as I explained earlier to you. The reason has to do with the specific heat capacity. Water has high specific heat capacity, so it will require more heat energy to be absorbed or to be taken out to change its temperature to 1 degree Celsius. And because of that, industrially, in the industries, whenever you want to store heat energy, it is kept in water. Because if you put large amounts of heat energy in water, it takes time to give the energy out. If you give it to solids, in no time it will cool and you will lose it. But water gives it out gradually. So if you want to store thermal energy, give it to water, because water has a very high heat capacity. Charlotte.
No, Mr. Dear.
Mr. Charlotte.
It's like I'm getting a bit confused.
Ask.
Okay, so you see, when you're heating like water, I mean it's just the gas, then you light it, but then it's still able to get like become hot. So how come like a whole sun, like you see how hot the sun is not able to like heat up like a water body? I don't get.
Yes, it is simply because, Charlotte, look at the instance you gave. Your water on the burner, and then this water body. The water body, river, whatever, or the pond has larger mass. So the number of molecules or particles of water here is very large. The reason why your gas can easily heat up the water in the cooking utensil, but the sun cannot easily heat up. It has to do with mass. Are you okay?
Yes, please.
If you have the same mass in your kitchen, we'll see whether you can the burner can easily heat it. All right, please, is there any other question? Okay, Kelvin.
Sir,
Mhm.
please can you say the water will boil because of how direct the heat is, the substance.
You are talking about proximity. Yes, it's true. The water is closer to the source than the sun directly, but yes, that is true. But the mass is also a huge factor. Okay, in the case of the pond river, we are looking at huge volume of water. Is that okay?
Okay.
All right. And so that is it. And this also explains the reason why the temperature of communities around water bodies is moderated by the water body around. The breeze, land breeze, sea breeze. Okay. So because water has very high heat capacity, in the evening, when everything has suddenly cooled down, the stones, the metals around your houses and all that, then water would gradually be given out, liberating the heat energy. Okay, absorbed. And so when everything has cooled, water will be releasing the heat, thereby controlling the temperature of the surrounding, because it is now giving out the heat energy that was absorbed during the day. So this brings about what we call the breeze, the land breeze, and then the sea breeze. Okay. All right. So that is it with heat capacity. So the Charlotte.
Mr. Dia, so during the evening, it gives out the heat, and then by morning, it is cold, right?
So what happens is that that is it. During the evening, because the weather is so cool, and then the temperature of substances or materials around, especially solids, have suddenly dropped, okay, there will be transfer of heat. No, heat energy is the energy that can be transferred from one body to another body due to temperature difference. So because in the evening, you have dropped your temperature, water has a higher temperature, and so there will be transfer of heat due to the difference, okay, on and
Yes.
on. So in the evening, the water bodies will be controlling the temperature of the surrounding because there will be transfer of heat energy. Then in the morning, what happens is that in the evening, it has given out the absorbed heat energy. In the morning, it will be absorbing heat energy again. So when the sun comes, then it will be absorbing it, but it will absorb it gradually because it has very, very huge heat capacity. Okay. So when
Yes.
you are hot enough, water is not there yet. It will be absorbing gradually. That is what happens.
Yes, please. Thank you.
So knowing the temperature of substances, the temperature of the specific heat capacity of substances, you can easily identify the substance because different materials have different heat capacities, and this is due to their difference in atomic compositions. Is that okay? They are different, and so they will certainly have different. Now, heat energy is such that when a body is at a higher temperature, it will transfer heat energy to a body at a lower temperature. So if you have two substances, A and B, and then maybe substance A has a higher temperature than substance B, what happens is that, so let me illustrate something. Material A, temperature T1. Material B, temperature T2. T1 is greater than T2, there will be transfer of heat energy from T1. So the heat energy will be transferred in this manner from T1. Okay. Then this transfer will go on and on and on and on till the two have attained the same temperature and the transfer will cease. Okay. So whenever two substances have different temperature, okay, there will be transfer of heat energy from the body at a higher temperature to the body at a lower temperature. This transfer will go on and on and on till the two have attained the same temperature. When they have the same temperature, then the transfer will stop. At that point, we say that the two bodies are at thermal equilibrium. Okay. So when the transfer of heat energy ceases, the two bodies are said to be at a thermal equilibrium. A thermal equilibrium. So, what do you understand by thermal equilibrium?
Thermal equilibrium is a point at which the temperature of both objects are the same.
So good. So it is at a point, okay, where two bodies in thermal contact. When two bodies are said to be in thermal contact, it means they are such that they can share energy, heat energy. So when one body has a higher temperature than the other, then heat energy can be transferred from the body at a higher temperature to the body at a lower temperature till they attain thermal equilibrium. And that is the point where they have the same temperature and it will stop. Now, it is like when you mix cold water and then hot water. So this is a container partitioned. This side of it has cold water and the other side has warm water. The moment I remove the partition, there's a partition. The partition separating them. When you remove it, they will begin to mix. But what will happen is that there will be heat transfer from the molecules at a higher temperature to the molecules at a lower temperature. So there will be transfer. The transfer will stop when the two have attained the same temperature. So T1 is the initial temperature of the cold water. T2 is the initial temperature of the warm water. When you remove that partition, you realize that the cold water will be, because the transfer is in this direction, the cold water will be gaining, whereas the warm water will be losing heat energy. Okay, then this will gain, this will lose. But the moment the temperature of the two is the same, it's like this one is giving to this. So you are gaining, I'm losing. When So initial, this must be this T2 must be greater than T1. So this will drop, this will increase. Drop, increase. When they are the same, then the transfer will stop. At that time, you realize that the temperature of the mixture will be greater than T1 because this will gain. Okay, the temperature of the mixture will be greater than T1, but the temperature of the mixture will be either less or equal to T2. And it must be actually equal to, because it will stop when they are at the same temperature. Okay, but usually in the equation from this side. So the final temperature must be greater than T1 because T1 is what is doing the gaining. Okay, then T2, the mixture must either be less or equal to the temperature of the warm water. This is what happens whenever heat energy is transferred from one body to another. Please, is there any question? But this thing occurs on condition. The condition is that the two bodies in thermal contact must be in an isolated system. Okay, they must be in an isolated system where no heat energy is transferred from the system to the surrounding or from the surrounding to the system. Here, this is the system. Whatever is understudy is the system, and the surrounding is the area or region around it. So whenever two bodies are in thermal contact and heat energy can be transferred in this manner, depending on difference in temperature, then the system must be in an isolated state where no heat energy can be transferred from the system to the surrounding or from the surrounding to the system. Okay. And so this even explains the reason why, you see, when you touch somebody, when you hold somebody, there is a chances that if I touch somebody, I may feel cold. Then, then the next question can be, oh, are you sick? Asking the person whether the person is sick depends on what you felt. Maybe the body is too cold or too warm. When you touch somebody and the body is too warm, what it means is that the person is transferring heat energy from his or her body to you. And so you are gaining extra heat energy. Okay, so there's a transfer of heat energy from the person to you. So your total internal energy has increased. The reason why you are feeling cold. If you are feeling cold, then the person, if you are feeling warm when there's a transfer, if you are feeling warm, then the other person must be feeling cold. So if you have somebody sitting at your side, touch the person, feel the person. If you feel that warmth, then it means you are gaining energy from the person and it's added to yours. So the moment you feel that warmth, the person must feel cold. On the other hand, if you touch somebody and you feel that coldish condition, okay, then it means you are losing heat energy to the person, and so your net body internal energy is dropping. The reason for which you are feeling cold. If you feel cold, the person must feel warm. So whenever there is transfer of energy, the internal energy of the two bodies change. Whenever there's the transfer of heat energy, the internal energy of the two bodies will change. That is why when you feel warm, yours, there will be transfer from one person to you, and the other person will lose. Please, is there any question? Okay, Charlotte.
Mr.
No,
Dad,
please.
please. So does it mean that if someone is not feeling well, the person is like very, very hot. Like if the person sleeps beside someone who is cold, like the whole body is going to reach equilibrium where like they all share the same body temperature.
And then in this case, you see, it cannot, in the scenario you are giving me, it can't happen because I told you that for this to happen, you should be in a kind of isolated state or in a closed system. Okay. If you are not in a isolated or closed system, there will be heat energy from the system, which is you and the other person, to the surrounding, or you also be affected by the weather of the surrounding. So this thermal equilibrium thing occurs when bodies are in an isolated or a closed system. You got it?
Okay, the two people are in an isolated system.
Yes.
So it's going to happen.
Yeah, it will happen.
Okay.
It will happen. That is why we'll talk about the vessel. We are now even going to talk about calorimetry, and you see the factors or interventions that are made so that bodies exist in an isolated kind of system. All right. Please, is there any question? Is there any question? Let's try and solve a question. So I'm going to read. How much heat energy is required? How much heat energy is required to raise the temperature of 8.0 kilogram of aluminium, 8.0 kilogram of aluminium from 20 degrees Celsius to 25 degrees Celsius if the specific heat capacity of aluminium is 900 joule per kilogram per Kelvin. How much heat energy is required to raise the temperature of 8.0 kilogram of aluminium from 20 degrees Celsius to 25 degrees Celsius if the specific heat capacity of aluminium is 900 joules per kilogram per Kelvin?
Mr. Evia,
Hello.
please can you send that question to the group page, the platform? I just joined.
Okay, let me drop it there. So it's there. So
Thank you.
how much heat energy is required to raise the temperature of 8.0 kilogram of aluminum from 20 degrees Celsius to 25 degrees Celsius? Now, specific heat capacity of aluminum. It's 900 joules per kilogram per Kelvin. So I've sent you the specific heat capacity of aluminum too. Let me send a second question which will be answered. Okay, I'm sure you are true. Are we?
Please, should we start the second one?
Okay. Attempt the second one too. Maybe in 5 minutes. Let's see. So the second question also says that a 6.0 kilogram piece of iron at 100 degrees Celsius is immersed in 3.00 kilogram of water at 20 degrees Celsius. Determine the final temperature TF when thermal equilibrium is established. So you are determining the final temperature whenever thermal equilibrium is reached or established. So let's see how you can also try the second question. 5 minutes. Okay, 5 minutes. Let's see what we can do. And I've sent the specific heat capacity of water and aluminum, the ion, to their group. These are values. All right. So that is whatever, I think the values are correct. For the mass of aluminium, 8.0 kilogram, the change in temperature is equal to 25 minus 20. So this is 5 degrees Celsius. Then the specific heat capacity of aluminium is given as 900 joule per kilogram per Kelvin. Please, about the unit. If Q is equal to mc times delta T, and I want the unit of specific heat capacity, then it must be Q over m delta T. The SI unit of heat, thermal energy, is Joule over kilogram, then change in temperature, either Kelvin or degrees Celsius. So the SI unit becomes Joule per kilogram per Kelvin or Joule per kilogram per degree Celsius. Okay. Therefore, Q is equal to mc times delta T. We are looking for the quantity of heat energy that must be absorbed to raise. This time we are raising it. So 8 times 900 times 5 degrees Celsius, or this is also equal to 5 Kelvin, because change in temperature on Celsius and Kelvin scale is 1:1. So 4,500 times 8. And Charlotte, what did you make for that?
Please, 36,000.
So 36,000 joule or 36 kilojoule. Then the second question. The second question is that a 6.0 kilogram piece of iron at 100 degrees Celsius. So in the second question, we are looking at iron, the metal iron. Lizzie, are you there?
Yes, please. I'm having network problems, so it's going on and off.
Oh, try and fix it. So iron at 100 degrees Celsius is immersed in 3.00 kilogram of water. So now I have water of mass 3.00 kilogram. Its initial temperature is 20 degrees Celsius. And the iron at 100 degrees Celsius is immersed into. So certainly there will be transfer of thermal energy from the ion to the water in all directions. So water will gain. So if water is gaining, we expect the temperature of water to increase, and then the temperature of the ion to what? Decrease. Okay. Now, this lose-gain situation would continue till the two have attained thermal equilibrium. At thermal equilibrium, the two bodies would have the same temperature and the transfer would stop. Okay. Now, at thermal equilibrium, we expect the temperature of the mixture or the final to be greater than the temperature of water, and we also expect the temperature of the mixture or the final to be less than the temperature of ion. Okay, so let's establish the equation. So thermal equilibrium, the point of thermal equilibrium describes the principle of conservation of energy, that energy will never be lost or gained, okay, but it can be transferred from one body to another or one form to another form. So heat loss by ion must be equal to heat gain by water. This is at thermal equilibrium. So at thermal equilibrium, there is the equation. Heat loss by ion must be equal to the heat gain by water. Now, heat transfer is equal to MC times delta T. Okay. Then heat loss by ion will be equal to mass of ion times specific heat capacity of ion times the change in temperature. Then heat gain by water would also be mass of water times the specific heat capacity of water times the change in temperature. Okay. What is the mass of ion? Charlotte, what's the mass of ion given?
This is 6 kilograms.
So 6 times the specific heat capacity of ion, we are told is 450. The change in temperature, please, is always positive. What is the change in temperature of for the ion? The initial temperature of ion, which is 100 minus temperature of the mixture or temperature of the two at thermal equilibrium, which we don't know, TF. This must be equal to mass of water. What's the mass of water?
3 kilograms.
3 times 4,200. Now, what is the change in temperature? I said that when the ion is put into immersed in water, the water which is at a lower temperature will be gaining. So the temperature of water would be increasing. Okay, so at thermal equilibrium, the temperature of the mixture will be greater than the initial temperature of water. TF is the temperature of the mixture. Okay, but because the temperature of the mixture is greater than the initial temperature of the ion, this will be TF minus 20. So the final temperature, which is greater than the initial temperature of water, minus 20. But here, the initial temperature is always greater than the final temperature. So 100 minus TF. And then TF minus the initial lower temperature of water. Charlotte.
Mr. Jia, please, can you come again?
Okay. So I want to create a scenario. Charlotte, you have water. Okay. Water in a cup at maybe 10 degrees Celsius. Another water is heated, then poured into your water in a cup. So when this transfer is done, Charlotte, compare the final temperature when the hot one is added to the initial temperature. Which one will be greater?
The final one.
The final one. So if we are looking for change in temperature for the water, because the final is greater than the initial, we subtract the initial from the final for the cold water. Now for the hot water, we heated the water to 100. So the initial temperature of the source is greater than the final temperature of the mixture. So for the hot water, if you are looking for the heat energy loss, it will be its initial higher temperature minus the final temperature of the mixture. Are you okay?
Not really.
We are looking for heat loss by the hot body must be equal to the heat gained by the cold body. Okay. What is the heat loss by the hot body? Mass of the hot body times the specific heat capacity times the change in temperature. How do we calculate the change in temperature for the hot body, which will be doing the losing? It is the initial temperature of the hot body minus the final temperature of the mixture. Are you okay?
Yes, please.
Then the body that is doing the gaining is initially at a lesser temperature. So its temperature change, because the final will be greater than the initial, you subtract the initial from the final. I'm sure you're okay now.
Yes, please.
So that is how to calculate the change in temperature for the one that is losing and the one that is doing the gaining. Change in temperature is always positive. So I think this 0 would cancel 1. 6 times 45. Quick one. Okay, 3. This 3 would also cancel this and will be 2. So we have 2 by 45 times 100 minus T final is equal to 420 times T final minus 20. I think 3, still 2 can go into this, and 2 would also go into this 21. Okay, so now we have 4500 I'm multiplying through minus 45 T final is equal to 210 TF minus 21 by that 420. Correct? Is that correct?
Yes, please.
Okay, so group the like terms and then find F for me. So when we group like terms, we have 210 TF plus 45 TF is equal to 4500 plus 420. Okay. So this is 4,920. So we have 4,920. Then this is 255.
Yes.
So let's divide through.
Three to 8 on 17.
Pardon?
3 to 8 on 17.
When you divide, we are looking for final temperature. So you divide 4920 by 255.
Oh, you want it in a decimal?
Yeah.
19.2941.
So approximately 19.3.
Yeah.
19.3 degrees Celsius. Let me check. So that is how to calculate for the temperature of the final temperature of the mixture. Okay, so please take your time, go through it systematically. Usually, as I said, the final temperature would always be less than the initial temperature of the hot body. But the temperature of the mixture would also be greater than the initial temperature of the cold body, because the cold body will be doing the gaining and the hot body will be losing. Okay, but the final one will always be less than it. Please, if you have any question, quickly ask. What you need to understand is the change in temperature and then how to establish this equation. Amma.
Miss Adria, please, I
Amma,
got a different answer.
you got what?
A different answer.
So what did you get? What did you get?
I got 34.12 degrees Celsius.
Yes, I think there's something wrong in this in some way. So please, the rest is mathematics. You can easily correct it. The answer must be that. I think 34. Okay, maybe something went wrong in okay, so you correct that and then let's continue. So calorimetry. As I said, calorimetry is the measurement of heat, thermal energy, using a calorimeter. So we are measuring heat energy, that is this heat transfer, heat loss, heat gain. Okay, so the principle of using the principle of calorimetry, we can use it to calculate the heat loss, the heat gain by materials. Okay. Calorimetry. So calorimetry is the measurement of heat energy. The instrument used is the calorimeter. In fact, calorimetry comes from a word we are so familiar with, calorie. Hey, you increase your calorie. Okay. I'm sure it is even out of that word that we have cholesterol and all that. So we use the principle of calorimetry to measure heat. And what is the principle of calorimetry? The principle of calorimetry states that whenever two or more bodies that is in thermal contact whenever two or more bodies in thermal contact dwells in an isolated state. There is the transfer of heat energy from one to the other until thermal equilibrium is attained or is achieved. So that's the principle we've been using. That when two bodies at different temperatures, okay, at different places or at different temperatures. When two or more bodies at different temperatures in thermal contact dwells in an isolated state, there is a transfer of heat energy from one body to the other until thermal equilibrium is obtained or attained. This is a principle of calorimetry. Okay. Now we use this principle to determine the specific heat capacity of substances, whether solids or liquids. Mostly for solids and liquids, because for gases we'll need a different, instruments or gadgets. But we can use the principle of calorimetry to determine the specific heat capacity of liquids or solids. We can also use this to determine the final temperature of a very hot sources that isn't accessible, especially a furnace, a very hot oven or furnace, where you cannot approach or go close. We use the principle of calorimetry to determine the temperature of the surrounding. Okay, so that is the basics of the principle of calorimetry. Tomorrow we are going to look at how to use this to determine the specific capacity of substances, how to use it to determine the temperature of very hot sources which are inaccessible. Okay, then we go through some calculations on calorimetry. Tomorrow we must end calorimetry and then start a new thing. So we are going to go through it with some speed tomorrow. Please, how many minutes do we have to end today's show? Check for me. 2 minutes.
2.
Oh, okay. Then our time is almost ended. So please, I'll give you trial works. I'll send trial works to the group. Do it. Let me hear from you. Even if the going gets tough, try it and then get back to me. Okay. All right. Okay. So this is where we draw the curtains on today's meeting. I know you are going to prepare for other lessons. May the good Lord be with you and empower you to do my exercises. Until tomorrow, in fact, bye-bye.
Bye.
Bye.